Welcome to qnawire.
All right, we want to figure out the relationship between these two molecules. And we've got a few options. We've got that they are constitutional isomers, that they are identical, or that they are stereoisomers or different compounds altogether. Okay, well, right off the bat, I'll just say they're constitutional isomers. So if you're not interested in why, then that's your answer. Okay, so let's go on. Why are they constitutional isomers? Okay, well, what makes something a constitutional isomer is that it contains the exact same formula. Like if we were to just write the number of carbons, like this has 6 carbons, right? And then for hydrogens, it's going to have 6 plus 6, 12, right? This is C6H12 and this is C6H12. Okay, that doesn't mean they're constitutional isomers, though, right? Or it does mean they're constitutional isomers, but it doesn't mean they're only constitutional isomers. Consider that all stereoisomers are also constitutional isomers. For example, put a bromine here, and put a bromine here. We know these are enantiomers, right? But they're also constitutional isomers, right? The formula is going to be C4, C3, 6, 8, 9, H9, Br. That describes either one. So if something's going to be a constitutional isomer and not, like, if you say something's a constitutional isomer, that's usually because it's not a stereoisomer. Otherwise, you just say it's a stereoisomer. So what we're kind of asking is, like, we can tell that they're at least constitutional isomers. The question is, are they also stereoisomers? Are they constitutional isomers, identical, stereoisomers, which would also make them constitutional isomers, or just flat out different compounds? Well, I've already shown that they're at least constitutional isomers because they have the same formula. So now we just have to answer, are they identical? Well, no, because you can just see that they're different. They are clearly not the same molecule. You could name it and see that they're not the same molecule. This is going to be dimethyl, 1,1-dimethyl cyclobutane. This would be 1,2-dimethyl cyclobutane, except for this one would have some sort of R and S designation. In either case, they're not identical. So then we just have to answer, are they stereoisomers, right? How do we figure that out? Well, one hint right off the bat is that even though this first molecule has wedge and dash formalism in its drawing, it has no stereocenters. Remember, to be a stereocenter, you've got to have a carbon that has 4 unique bonds, right? And this carbon right here, it's got a bond to a methyl and a bond to a methyl. That's 2 of the same bond, so it doesn't have 4 unique bonds. This has a CH2 and a CH2, or a CH2, so that's not a stereocenter. And these both have CH2, so those aren't stereocenters. So if you have no stereocenters, you can't have a stereoisomer, so this cannot be a stereoisomer of the first, right? You could have cis-trans isomerism, but that's not one of the options. So, and in either case, this wouldn't have a cis-trans isomer for other reasons. So we've ruled out stereoisomers, we've ruled out identical, and because they have the same constitutional formula, C6H12, we know they're not different compounds, right? They're well, it's kind of weird they are different compounds technically, right? But I guess they're saying you can't be a constitutional isomer and a different compound at the same time, so that's fair. If you looked at that molecule on the left and then you looked at the following molecule. This is also C6H12. I would classify these also as being different compounds, but that's just not a great question. But yeah, constitutional isomers, that's the answer.